Finally, let's move on to surface area calculation. Remember in section 8.2.5 we learned some methods to compute the surface area when a certain object or a certain curve is rotated across the x-axis, as well as when it is rotated across the y-axis. So if it is an x-axis rotation, we used 2 pi y ds, and if it is a y-axis rotation, we used 2 pi x ds. And then we had two formulas for the value of ds, and we used it appropriately, right? And if the curve is expressed in the parametric format, also we have a very similar approach, right? So this same rule, when it is an x-axis rotation, you will have y here, and if it is a y-axis rotation, you will have x here. That rule is still there for the parametric relationships as well. Anyway, now if you don't remember this one, please go over to those videos and try to have a good understanding about this first, and then come back to these parametric curves, right? Then you will have a better, you will be more comfortable with these calculations if you have a good grip on these manipulations, right? Okay, so now here the result is, if the curve C is given with these parametric representations and the starting point is alpha, the end point is beta. See here, you have to notice that these alphas and betas represents the parameter, the starting and the end point of the parameter, not the x or the y coordinates. Okay, so here we are using those starting points and end points of the parameter, right? And we are integrating it with respect to t. And here, if it is a x-axis rotation, we have y here, and if it is a y-axis rotation, we have s here. And for ds, no matter whether it is an x-axis rotation or a y-axis rotation, we are going to use this term, right? So basically what we have is 2 pi x ds for y-axis rotation and 2 pi y ds for the x-axis rotations. And for ds term, we are going to use this complete thing no matter whether it is a y-axis rotation or even if it is a x-axis rotation. And in the next video we will go over an example.